So welcome back, this is 6.5. This is the graphs of polar equations. You'll notice that in this lesson we're using Desmos instead of, say, a one-note notebook. That's because primarily all we're doing in this lesson is looking at graphs and analyzing them and seeing what we can do with them. The problems and the questions are just like in 6.4, almost identically, except we're just now extending these ideas to see the fullness and the full ability that we have with polar equations and what we can do with them. So let's jump in and see the full depth of what we can know about a polar equation when we analyze it. There are two sections to this lesson. There's first an analyzing curves and seeing two specific things I want us to notice about analyzing a curve and how to look into it. And the second thing I want us to look at is just the types of curves. What can we make with polar equations? What are some cool shapes we can do? And so we're going to look into those as well. So let's go ahead and start off with curve analysis. Now this Desmos book, equation sheet, whatever you like to call it, is on the OneNote notebook, and it's in the description of this video. So go ahead and I encourage you to jump in and pull up this page as well, so you can work along with me and test out. And when you see something, when you see me do something, try it out for yourself and mess around with the values and see what you can do. You know, just play around with this a little bit so you can kind of feel the intuition behind why these things work. Now let's go ahead and jump into curve analysis. In curve analysis, we have two main ideas. One is symmetry, and the other one is maximum R, finding the maximum of an R value, the maximum radius we can have in an equation. So the first one is symmetry. Let's go ahead and look at that. So we want to look specifically at the symmetry of an x across the x-axis. So I've got this graph here. I've got this graph here, and it looks. We'll go into a little bit pretty soon what this graph actually is and what it means and how to create one of these. But for now, let's just go with the fact that I have a graph that's r equals 1 plus 5 equals 1.5 plus the cosine of theta, and it looks something like this. Now here's something I want you to think about. What if I was to take, so let's say I was to take a point. I'm going to zoom in on a point right here so you can imagine which point I'm trying to look at. This point right here about 1.35 and 1.9, right in that range. So let's take that point. And let's say I was to I created a radius from 0 to that point, and I had a certain degree theta that got me there. What would happen, you think, if I'd made that theta negative? If I went the opposite direction, instead of going upwards, I went downwards with theta. Well, if I were to do that, it would get me a point down here, somewhere roughly in this area. And you can see it's the exact same point, just on the opposite side of the x-axis. And that's really what symmetry is on the x-axis. Any point that's above the x-axis equals the same point below the x-axis. And so we know that something has symmetry across the x-axis is if we can go both above and below the center with theta and get to two separate points. If every single point above the x-axis can be mapped to a point below the x-axis, and if we switch theta, we get from one point to the other. And so we can see that. So if I was to take this equation, we can see this with the second graph. If I was to take this equation and make it r equals 1.5 plus the cosine of negative theta, I would get something like this orange equation that looks the exact same as the first one. And you can see that if I was to, and the reason why is because the points that used to be on top are now on the bottom, and all the points that are on the bottom are now on top. And so they create the exact same equation. I encourage you to mess around with some of the other formulas in this equation set, and to show yourself, hey, this doesn't actually work out in other equations. Like for example, if I was to go to this equation here, I've got two other equations that are symmetrical about the origin. If I was to make one equation, the negative r times this equals the square root of sine times 2 theta. If I was to make it negative, that would not create the same equation. But you see what happens. All the points above theta go below now, but they go in this really weird distorted view. You're welcome to go and play around with this to think about why this works the way it works. But the point is, if everything mapped above theta is a point, and everything that the opposite theta is also another point, well then we know that it has to be symmetrical about the x-axis, because they create a mirror image. Cosine becomes a mirror image. So that's the idea. If you switch theta from positive to negative and it creates the exact same graph, then you know it's symmetrical about the x-axis because all the points are flipping. Great. Let's look at symmetrical about the origin. What happens if I took this graph here? You kind of see where I'm, probably can imagine where I'm going with this, especially because of the title. What if I zoomed in on a point, say this edge point, let's say the very, very edge, this furthest point that R can go out to. It's roughly at 0.65 and 0.75, somewhere around that range. The y value of 0.75 and the x value of 0.65. If I was to take that point, and instead of going out, so it's at some degree, say maybe 45 degrees, and it's at some distance, say maybe 1.5, and if we were to, or maybe just 1, and let's say we wanted to go the opposite direction. Instead of going out, I wanted to go back. Let's say instead of going out to here, I decided to make r negative and go back. Oops, and go back down to, say, this point. If I can do this with every single point on the graph, then I know that it's symmetrical about the origin. If I could go to, say, this point over here, and this 0.38, and I don't know, less than 0.3. If I went all the way down to down here, and I could find that same points, then I know that every point maps to its corresponding points that's reflected around the origin. Remember what reflection around the origin means? It just means that if I were to turn it upside down, it would look exactly the same. Remember odd functions. An odd function is a function that has an odd exponent, like x cubed or x to the fifth. You know, these things are symmetrical at the origin because we can flip them upside down and still create the same equation. And it's the same thing here. So if I can make r negative on every single one of these points, and you'll hit another point, then I'm good to go. And we see it here. If I was to make r negative r equals the square root of the sine of 2 theta, then we can see that every point maps to another point on the curve, and so therefore it is symmetrical about the origin. Every single point can do that. Every single point can make that symmetry. Okay, if that doesn't make any sense, if that doesn't make enough sense to you, again, just mess around with these equations. Try to see the intuition behind why this is working. I encourage you, the more you do that, the more this natural intuition comes, the more powerful this tool becomes for you. All right, so that's symmetry about the origin. What would happen instead of moving things back and forth across the radius, or just flipping the radius or flipping theta? What if you flip both theta and the radius? Let's go ahead and see that over here. And you can probably guess where this is going now, especially because of titles. So if I went to this corner point up here, let's say it was about 0.52 and 0.86, something along those lines, and I was to flip the radius, so I was to make it to go the opposite direction on the radius, I would get a point somewhere out in this nether region, down here, somewhere down there. And that makes sense. So we go from over here, roughly over here, to all the way down here. All right. Now what happens if I was to take that angle, whatever resulting angle is there, and flip the angle? If I was to flip the angle as well, then I'd go from down here, and I'd bounce across the x-axis. And I'd bounce across the x-axis. I get a point way over here. And if I was to do that, and you can kind of see at the resulting points that comes from it is the point that's on the opposite side of the y-axis. So if I was to take any point and flip r and flip theta, then I would get its corresponding point on the opposite side of the y-axis. And you can see that with this graph. If I was to take all the points of this graph, you can see this graph specifically is symmetrical about the y-axis. So if I was to take every single point and flip r and flip theta, you can see, well, I create another graph that's exactly identical. So this we can derive from this then the fact that if I take the reflection of r and the reflection of theta and do it with every single point on the graph, then boom, I've got and create something that's the exact same, that I know that's symmetrical about the y-axis. So these are all helpful tools to know. And again, please just start messing around with this. Figure out more of this on your own. Like take the symmetrical about the origin. If we take this other graph, this graph here that I haven't defined yet, and if I let's see what happens if I was to do more than just reflect it across the r, just reflect around the origin, just change r. This is clearly not symmetrical on the y-axis. So if I tried to change theta, try to make it, let's say this was minus 2 theta, you can see that it creates, well, something that reflects across the y-axis, sure, but it doesn't create what we want it to create. It doesn't create the same points. It creates something reflected across the y-axis. And so you can see that this would not work. We can show here this is not reflected across the y-axis because it creates completely different points. But you can see all the points are reflected across the y-axis. So again, play around with this. See until it kind of really clicks in. Cool. And assuming it did click in, let's go into the last part of this section called maximum R values. So let's say I have an equation like this. This is another one of those funky circles that we'll explain pretty soon. So let's say I have this circle-ish curve, and I want to figure out where's the points when of theta. At what point theta can R be the greatest it possibly can be, or just in general, when is R furthest from? When is the radius furthest, the biggest? When is the highest? When is it the largest? And you can kind of see. I'll give you a second to think about that. When is R the biggest? And if we look at it, we can kind of see, well, okay, the place that R is largest is when it goes furthest out from the origin. That'd be this point down here, this 4 right down there. That's when R is greatest, when greatest when it hits 4. Now, but what about the theta? At what point theta is R greatest? We don't really know that because we can't really see how much of theta we've graphed. We don't know how large theta is. It's just we don't really know. There's not a very visual representation of what thetas are graphed here. We can kind of see what x's have been graphed and what y's we have graphed. We don't really know how much theta we've graphed. So if we were to, but we can change this though. If we were to change this equation up a little bit, we can see exactly what theta, how far we are in theta and what theta does at any point. So if I was to replace, if you can see in this lower equation, if I was to replace r and theta with y and x, for every single input of x, we would get the same y as we would r. Let's say that another way. If r equals 2 plus 2 cosine theta, and I plug in any value for theta, I'll get some value r. If I plug that same value in for x, I'll get some value out for y. So ostensibly, if I was to change these variables with y and x, and then find the maximum find the maximum y there is, then I'll know the maximum r. And if I find the maximum, and if I know where the maximum y is, well, then I can figure out where the corresponding x point, and I can figure out where it's placed. Let's try to make this a little more concrete. Let's go ahead and graph this graph. You can see this graph looks very, very different from the normal curve. Now, again, that's because instead of using a radius and a theta, we're using y and x. Again, these create the exact same values. You can see that when we have 0 for theta, our r value, if we were to calculate it out, would actually be 4. So we have this, that's what creates this 4 value down here. And we can see that on this graph up here. If I put in, when we have 0 for x, the y value is 4. So it jumps all the way up here. So we know that the r value, or this y value, hits its maximum when x is at 0. We also see that the y value hits its maximum between 6 and 7 over here. And we could use pi and radians in order to help us figure out exactly what that point is. But for the sake of example, let's leave it there. And we can kind of see that every single time it has a sign, it's a sinusoid. It can have that kind of pattern to it. So similarly, we know then that when theta equals 0, then the radius has to equal 4. And if theta were ever to hit this roughly 7-ish point, then the radius would also be 4 again. You can probably imagine it would go around all the way around the curve and come back. And so that's exactly what we see here. If you want to find the maximum r value of something, go ahead and just plot it as y and x instead of r and theta, and then see where x hits, well, see where the y maximums are, and then figure out what x values there are that create that. And from there, you'll figure out exactly what theta values you need in order to get the maximum radius values. So that's what that is. That's the maximum r values. Now let's go ahead and see what happens if we try to, now that we've gotten through this and we've kind of analyzed curves a bit, let's just go and jump in and talk about a bunch of different types of curves. Now the most basic kind of curve that we have is just the radius. Well, there's one's more basic than this, but we'll get to that in a minute. the most basic curves are just r equals sine of theta and r equals cosine of theta. Now imagine what happens if we have r equals sine of theta. That means, let's think about this. What does it mean when r equals sine of theta? Think about this for a second. Now, assuming you've thought about it, the r equals r equals sine of theta means that we're going to take every single value of theta that would on the unit circle, and we're going to, or every single value of theta for any circle, and its corresponding y value will be our radius. Remember, again, the coordinates of any point on the unit circle are cosine, sine, and so sine is our y value on the unit circle. So what the radius is the y value of every theta on the unit circle. And we can kind of see what that looks like. Let's try to get a more generalized picture. This would be, you can kind of see what happens here. If I was to make theta 90 degrees, for example, we know the sine of that. The sine of 90 degrees is 1. And because the sine of 90 degrees is 1, if I was to turn up 90 degrees, I would and go the full direction, I know that I have to go one distance. So we go 90 degrees and 1, and that would get us this point up here. So we turned up 90 degrees and we went one distance, that'd be this point over here. If I went down to, well, 0 degrees, I would get this 0 point down, I would get 0. 0 degrees on the unit circle is just 0 for sine. The y value of that is 0. So we get 0 here when we have 0. So, and things just oscillate from 0 to 1 to 0 to 1. And so that's kind of what we're doing here. The radius is just the y value in the circle. And so let's see, that's what that is. Now let's try to imagine here what you think the radius of the cosine of theta would be. What do you think would happen if we did that? Well, if we really looked into it, if we experimented with it a little bit, we would say, hey, well, r equals cosine of theta. If we plugged it in, we'd get the same thing except on the x-axis. In fact, if you were to rotate your screen right now, I don't know if you're watching on a phone or on a laptop, I probably wouldn't recommend rotating your laptop, but if you were to rotate your screen right now, you'd kind of see it looks the exact same, except it's just on the x-axis. If you rotate it so the x-axis becomes the y-axis, it looks pretty much like the exact same thing because it's doing the same thing. It's just the x value on the unit circle. When x equals 0 degrees, when theta equals 0 degrees, well, on the unit circle, when theta equals 0 degrees, then the x value of the corresponding point would be 1. And so in this instance, when x equals 0 degrees, we go all the way to this point over here, this one point. And it goes back to 0, we hit 90 degrees, and we kind of just go back and forth again like that. We create this circle. So that's the basic curve. From here, we're just going to manipulate this curve a bit and just see what happens. What happens if I was to take it and say, what happens if I was to take, say, the cosine, and if I wanted to make it 2 times the cosine? Well, it would just be twice as big. When x is 0, then it'd be 2. It'd be whatever when theta is 0, then we have 1 for cosine. Multiplied by 2, we get 2. And we just kind of oscillate from 2 and 0. So this first variable kind of makes it bigger or larger, or it's bigger or smaller. We also make it 0.5. We'd have 0.5 the size of a circle, and so on. So let's just keep this at 1 for now. Now let's see what happens. What would happen if I did that and I let's say I made it 2, and then I decided to manipulate the theta itself, and I made it say it's 2 theta. Well, I guess it's something really interesting. This weird rose petal looking thing. And for the sake of your time, I'm not really gonna go too deep into why this rose curve looks the way it does, but I wanted to show you a little bit of how it works. So let's say I have the rose curve, and it starts out as r equals 2 times the cosine of n theta. If I was to make n a bunch, I can make n a bunch of different things. If I was to make it 1, it would look like this. If I was to make it 2, it would look like what we're used to. If I was to make it instead to be 2, let's say 2, and suddenly we have this clover-looking thing. And so you can see that the number of petals here is twice as many as this number. So you kind of think then, well, every single time I go up in theta, I'm going to have or every single time I multiply theta by a number, the resulting petals will be twice that number. But it's not quite, it doesn't quite work out that way. So if I put in 3, you'll see, hey, there's only 3 petals. But if I put in 4, well, it'd be 8 petals. And you kind of see that the more I change this, if I put in 5, I get 5. If I put in 6, I get, well, that's 1, 2, 3, 4, 6, 7, 8, 9. That's 12 petals. 7, there's only 7. So you can kind of see a trend here. Again, I encourage you just to mess around with this and experiment and see why this works. But for the sake of your time, I'm not going to go too deep into why this works the way it works right now, because it's rather complicated. But the point is, what you need to know here is with the rose curve, if the thing multiplied by theta is odd, it's going to create that number of petals. If it's 5, or it's 3, or if it's 1, or if it's 7, or if it's if it's 9, it's going to create 9 petals. As far as it's going to create that many petals. If I have an even number, say 2, it's going to create twice that many petals. And you kind of see what's happening a little bit, because if I have 2 petals, then suddenly it's not really creating. It's not like it's necessarily creating 4 petals per se, but you can kind of think of it as making 2 figure eights. And so it's got these 2 figure eights, and if I have 4, I've got 4 figure eights, and if I've got 6, I've got 6 figure eights. I've got 8 figure eights. That's sort of what's going on here. Now, if I have an odd number, I can't really create a figure eight too well. I can only create like half a figure eight, and so because it can only create half a figure eight, it only has 7 petals. It only has like 7. It only has if I did, let's say 5, I only have 5 half figure eights. I can't have 5 full figure eights. So that's kind of what's going on here. Again, mess with it. Maybe see what happens if you try to put in like 0.5 and just play around with it and see what happens. So that's what a rose curve is. You also notice if you're astute, you might realize, hey, this doesn't even look like a rose. It looks more like a daisy. Yeah, well, it does. It's just what they named it. If you look at a cathedral, like it says in the book, if you look at a cathedral, many cathedrals are called rose-stained windows, and it's just a name for it. It's not a good name, but it's the way it is. I'd rather call these daisy curves, but we'll leave it there. We'll leave it there. The next kind of curve is it kind of takes this and it kind of takes it a different direction. So it says, what if we didn't maybe multiply theta by something? What if instead we added something to the equation? What if we left that alone? Maybe multiplied theta by something. Let's say we had our curve, and let's say we added something to it. So if I was to add something to it, that would create something it creates what we call a Limaçon curve. And there's supposed to be a little tiddly underneath the C in the Limaçon. But for the sake of this, I couldn't really go too far into it. And I want you to take a second and really see what's going on in this curve. We have special names for every single section of this curve. Right now, this is not really a Limaçon curve. This is just cosine of theta. If I was to let it go on for a little bit, you'll see, hey, it looks like there's a curve inside of a curve. And that's exactly what's happening here. We call this a Limaçon with an inner loop. There's some sort of inner loop. And this is whenever we take that variable we're adding to it and divide it by that second variable. Right now, I made the second this one here. If we take this a and divide it by whatever this second variable is, whether it's 2 or 3 or not 235, 2 or 3 or 3 or 5, that kind of determines what's going to happen with this curve. Now, I'm just going to keep it 1 for now for the sake of simplicity. But remember, we're going to divide a by that number, whatever that number is. If the resulting number that you get when you divide a by that number is something is something less than 1, you kind of get this curve inside of a curve. You get a circle inside of a circle. And you can kind of see as it gets larger and larger and larger, it gets smaller and smaller and smaller until it just about hits the origin. And you can see right now, just about hit the origin when the curve just touches the origin. And we call this, when it hits this origin like this, when the resulting ratio is 1, this is well, it has 8.992, so it's close enough. We'd call this a cardioid. And you kind of see it's a cardioid because if you were to turn your screen again, you kind of look, or tilt your head, you kind of see, hey, it looks kind of like a heart. It looks kind of like a cardioid vascular part of your cardiovascular system. So we'd call this a cardioid. Now if we just kept this continuing, if we let A get bigger and bigger, and that's the ratio between A and, well, in this case 1, get larger and larger, we'd say it starts to go even further. Instead of making another circle, it kind of just starts to bow out a bit, and we call this a Limaçon with a dimple, or a dimpled Limaçon. Looks kind of cute. So it has this kind of dimpled look to it, and then it stays like this until it just about hits 2. And once it hits 2, it looks like it almost becomes straight, almost flatness. Now it's not a perfect circle, but it's pretty darn close to a perfect circle. And so we'd call this instead is more of a convex Limaçon, a Limaçon that kind of bows out now instead of somewhat bows, has this dimple thing to it. And so from here on, from 2 beyond this, from everywhere from 2 forever on, then it just looks, it's bowed out, it's convex. So again, if I was to take A and replace it with say 2, and had 2 plus 2 times the cosine of theta, it creates the exact same thing, just twice as large. So this is the ratio of this is still 1. So this, the ratio of 2 divided by 2, the A divided by the B, which in this case is a 2, this would be 1. So this would be a cardioid. So it matters not just what A is, but the relationship between A and B. And this B, we'll call this, just to be clear, this is a B, or B. Now, but for right now, I'm going to keep this as 1, just so you can mess around with it on your own. Okay, so that's a Limaçon. There's 4 different stages. When it's got that inner loop, it's got a cardioid, it's got a dimple, or it's convex. Cool. And that's our Limaçon curve. Now, we've got into pretty much let's before we get to that next one, let's skip on to the second to the last one, or to the last one. This is called a Lemniscate. I believe so. I believe it's called a Lemniscate curve. You might want to check out on the pronunciation of that one. This one can go 2 different directions, whether it's sine or cosine. Excuse me. Now with a sine or cosine, it can go either. You'd think it would. This one's going left and right, so you'd think that the sine would be going up and down. Again, this is it's such a wonderful thing to just explore and to look at. But if I were to put it in sine, I don't know if I can just type in sine here. S-I-N. Right. It would create something very, very different, actually. And again, I don't have time to explain this. For the sake of your convenience, I'm not going to. But I'd like you to see that it has these 2 different kinds of forms. Now, if I was to take this curve, and the real big factor about it is that we squared r. Now and in this case we had to square root both sides in order to make it actually fit into a graph, and graphable. So we have r equals something. But if I squared r here, I'm left with a something times the cosine of, say, we squared r and we made theta doubled, so we did double theta, and then we squared the coefficient. So it's r squared equals some coefficient squared times the cosine of 2 theta. That creates this really weird curve. And it's kind of a fun curve. And you can kind of see it, but it's pretty basic in what it does. It either gets larger, or when you affect g, it only just gets larger and smaller. Again, you can't really change 2 theta. I would encourage you to try changing 2 theta to see what happens. But if you change the 2 in theta, or if you change r, if you change anything else, it makes a completely different curve. But as long as you keep it to g squared, and you change this variable g, then you can have this really cool lemniscate or a curve. And that's what that is. The last one I really want to show you, and one I kind of saved for last, is something called the spiral of Archimedes. And this was my favorite curve because it's really cool because it's not only, well, let me just show you. This is r equals theta, so it's the most basic. It's probably super old because, I mean, what is super old? Because it's called the spiral of Archimedes. Archimedes found it, and it creates something really wonderful. Look at this. Look at this. It's huge. So it just runs right off the edge of our screen, and if we look at it more deeply, it's just this unending, unbounded curve of wonderfulness. Now I've bounded theta a bit. If I made theta, like, I want to make theta something huge, let's make it like how far can I go? Yeah, all right. So let's make theta something. Oh, is it stopped? Let's see. Can I, is that the limit of what I can do? Maybe I've hit Desmos graphing limits, but that's okay. This is a cool curve. It's unbounded. It goes on forever. It just spirals into eternity, and it's wonderful to look at. To think that the amount of theta we have is going to be the radius. It does so many cool functions. We can look at it and it says, oh, it's got a domain of all real numbers. I can plot at any x has a value, every y has a value, or multiple values at that, infinitely many values at that. And it's cool. It's continuous. It's symmetric about the y-axis. It's unbounded. There's no maximum r it can have. It's got no asymptote. It's just a great curve. And if I can go to my friends and spin my phone and then make them all hypnotized and stuff or whatever, I love it. Anyway, hope you find that helpful. The only difference, and again, the only difference in homework is just saying, okay, where is it's just using these graphs and things we've learned in these graphs. Like, for example, you want to remember that with a rose petal, every single time you have, or rose curve, all the odd petals will have, well, the odd number of petals will have that same number coefficient. The even number of petals, or the number of figure eights you have, is the number that's the coefficient of theta. Things like that. And that's about it. I hope you enjoyed the homework. I think this is one of the more fun lessons, because we could just play around with a bunch of graphs. So I'll see you in the next video. Oh, and one more note for the rose curves is something rather important. If I was to have, say, I need to zoom in. If I was to have a rose curve, say this is my rose curve. I made theta like 999. I shouldn't have done that. That was a problem. Oh, that's the problem. I made the rose curve theta at 999. If I go back and make this a reasonable number, even just 9 should be fine. Okay, so that's the thing. If I wanted to figure out how much theta I need in order to draw a rose curve, you can kind of imagine what it would take. I could, let's see, I've got a function. I'm going to put in pi here, if I even know where pi is. If I were to put in pi here, you can, let me just tell you, because I don't want to waste your time. If I have, in this equation, I would only need pi in order to graph this, in order to graph this equation here. If I have from 0 to pi for theta, that will graph the entire equation. Now, if I was to go to n equals 4, you might notice, well, if I knew where pi was, I could show you this would only graph half the equation. I encourage you to maybe just type in pi to your, maybe I can type in pi. Can I do that? Let me see here. Let me see. And a second. Yeah, if I can type in pi, then you'll see that it only graphs really half the curve for an even function. And the reason why this is, again, this is something just to mess around with and play with. If you look at this, and we graph up to pi, there we go. We only see about half the curve. And the reason why is simply because, well, if you're going to graph twice as much stuff with an even function, so if I want to graph twice as much stuff, I need to have twice as much theta power. You know, if n is just 3, I can graph all that with just 1 pi, because I don't need as much theta power. I don't need as much theta curve magic juice. I mean, the rest of this is just fine. I don't need much to get it all through. So that was just something I wanted to point out. If you have the size of the curve really shows you how much theta you need in order to graph it, and with these odd or even curves, it's probably always going to be pi, or in this case 2 pi, with pi being odd and 2 pi being even. So there you go. Hope this helped.